Let's say a few words about applications of double integrals. One of the simplest is finding a computation of mass. Suppose, for example, you have a density function. This density function is defined over a region, and it's a planar region, so we would be talking about things like units, grams per square centimeters, or ounces per square inch. This would be a planar density. If you take the density function and you integrate it over a domain, what you're doing is computing the mass of the domain. So in particular, if you have this region, every little dA, in other words dx and dy, is being multiplied by this density function to get a little bit of mass. And you could set this up with the Riemann sum if you really want to. And in the limit, you end up integrating or accumulating the mass so that you have total mass. By the way, the traditional notation for this is rho, which is borrowed from physics and engineering. We're going to be using rho later for spherical coordinates, so I always prefer to use delta for density, and so that's my preferred notation. This application simply means someone needs to give you a density function and ask you for the mass, and you do a double integral. So that's not too terribly interesting or exciting. One of the more interesting aspects comes when you start to find centers of mass, which begins with a computation of moment. Take a look at this. This is mx, and it is the moment over the domain of the moment with respect to the x-axis, okay? And you might be saying to yourself, well, if it's the moment with respect to the x-axis, why is y in here? That's not too complicated. If you look at this distance, basically the moment arm with respect to this x-axis, this is y, because this is the coordinate xy, where you're doing the location of the element that you're integrating, and you're using y to measure the distance to the x-axis. Similarly, if you want the moment with respect to the y-axis, you do another switch. So if you can do those computations, if you're given a density function and you're told which moment you want, you can simply compute it. The main application for the center of mass says, if you want x bar, the average of the x coordinates with respect to mass, you simply take my, because that's the one that has x in it, and you divide by m, where m is the mass. And similarly, y bar is going to be mx over m. And the sad truth is that most of the mistakes people tend to make with these is to get these reversed, and they forget that they need to compute mx with a y in it and my with an x in it. If you've got those down, you're in pretty good shape. By the way, there is another moment that we're very interested in, and that's called the moment of inertia. And I'm going to focus on this one, I sub 0, or I0, which is the moment of inertia about the origin. That one is the double integral over the domain, over the region, of x squared plus y squared multiplied by the density function and integrate it with respect to area. You'll notice something right away. This guy right here, x squared plus y squared, we totally want to do this in polar coordinates whenever possible, because x squared plus y squared is r squared, and this is usually the way we like to compute these. one more application that I'm simply going to draw out right here. Let's suppose we're looking at this integral. Double integral over a domain, and this time the integrand is the square root of 1 plus fx squared plus fy squared. Doing it with respect to area, and I'm going to give this a name. I'm going to call it S. You may already know what this is. This is the surface area integral. If you have the domain here in the xy plane, and above it you have some function z is f of xy, then above the domain you have a subset of this surface, and you might want to compute its surface area. If you're wondering where this came from, there is of course a derivation in the textbook, but I want to remind you about something. Remember little s? Little s was arc length. If you had a function y equals f of x, and you wanted to know the arc length from A to B, so this distance right there, you took f prime, squared it, added 1, took the square root, and that was the integrand for your arc length. Now that we're looking at a double integral over a two-dimensional surface, we have an analogy, okay? You simply take it up a dimension. If you want to ask me about taking it up a third dimension, let's not talk about that. We're just asking for trouble. The way this does work, for example, let's suppose we had a nice simple cylinder. And by simple cylinder, I'm going to say r is 2, okay, radius 2. And then we're going to take a function, z, which is a planar function, which is just 3 minus x plus 2y. So if I graph this, I would get a tilted plane, and it would slice an elliptical shape out of that cylinder. What is the surface area S? Well, if f of x, y, is 3 minus x plus 2y, we know fx is negative 1, and we know fy is 2. So going back to this original surface area integral, S is equal to the double integral over this region D, the disk at the bottom, of the square root of 1 plus, let's see, fx squared plus fy squared dA. In other words, the double integral over the disk region, square root 6 dA, or just square root 6 times the area of D. This is a disk of radius 2, so square root 6 pi times 2 squared, 4 pi square root 6. These are very elementary examples, and all of them will be revisited when we go to triple integration, so you're going to get another dose of them really quite soon.